So let's talk about the test. So the median grade on this test was a 72. So half of you did better than 72, half lower than 72. I know that sequences and series are very challenging. I shared the following anecdote with the last 3 people that turned in the test on Friday. When I took Calc 2 as a student 83 years ago, the teacher's policy was that he was going to drop your lowest test grade. And I don't remember how many tests there were, 4 or 5, but I'd gotten an A on all of the ones up until this last one, which was on series. And so I said, hey, I've already got my A. I don't need to study for this one. This will just be the one that I drop. That's the only time I've ever scored in the teens on a math test. So all of you did better than I did on this particular test. There is quite a range in terms of how you guys did on this test. The high grade was 99, and the low grade was a lot lower than 99. So here's what I'll say. You can do test corrections. You can get back full credit on number 4. The reason I'm making this call on number 4 is that several people interpreted this. Was it over x cubed, I think? Several people interpreted that as meaning this. And if you do that, then everything becomes 0 and the whole problem disappears. So it's not that. If you feel like you have to put parentheses somewhere, they're here, okay? So some people lost points on this for reasons other than that, but I've just decided I want to make it fair and open it up to everybody. So if you lost any points on number 4 for any reason, you can get 100% of those back. For the rest of the test, you can earn back up to 1/3 of the points that you lost. You can use your textbook, you can use your class packet, you can use any of our class videos. You can use your classmates. Apparently Rich wants nothing to do with you, so except for Rich. But I don't want you to use anybody that's not in this room, and I don't want you to use me, nobody in the math studio, right? Just each other. Any questions? And they're due Monday, start of class. All right? So we've got a full week. Any questions on the corrections? No, you can just do the corrections on the same test or on blank paper. Other questions?
Do engineers at NASA ever use infinite series?
That's a good question. Other questions? Okay, so again, we're on page 64. We'll take our quick look at the calendar. So I'm making a note right now. So today we're starting a brand new topic. We have only 3 more days of new stuff. Monday, Wednesday, Friday of this week is the end of the new material. All 3 days we're going to spend talking about something called differential equations, which we actually spent 1 class on near the early parts of this semester. Coming up on Wednesday, project number 9 is due. I have to remember to give that to you. Project 9. And that project, again, is just a reflection on the semester. It's not a math project per se. That's going to be due at the start of the final exam, right? So I'll give that to you next time. There is 1 more quiz. I'm not going to count it unless you feel like you need it to help your quiz average. But I'm just going to hand it out and not count it for most of you. Questions on the calendar? What? You need to decide whether or not you want me to grade it. Yeah. So if you want me to count it, I will, but you have to pick. Yeah, I mean it's a hard quiz. I mean like the. All right, so we're on page 64. We'll start with the daily summary. Dean. 64. Okay, thank you, Rob. Sam. Okay, so take a look. First of all, notice that all of our derivatives are dy dt. There's no x. T is often the variable because time is typically part of these problems. So dy dt in each of them. The first equation says you're looking for some function y with t's in it, so the derivative is negative t over 2. In part B, it's the same thing, but you want a function so that the derivative is negative the function over 2. You see the difference? The first part, the first differential equation is really easy to solve. Can you give me someone whose derivative is negative t over 2? Is negative t squared over 4. So just do an antiderivative of negative t over 2. But a completely separate answer, completely unrelated answer for B, you want someone whose derivative is the negative of the original function divided by 2. You can't just do y squared over 2. Y is the dependent variable here. In part C, even more complicated. Now we have y's and t's both appearing on the right-hand side. And then in part D, we've got a second derivative minus 5 times the first derivative plus 6 times the original function equaling 0. So let's, it says we'll solve A together. So let's try that. So if we take an antiderivative of negative t over 2, we said negative t squared over 4. And then we'll make it general by doing what? Plus c, right? That's what we stick on at the end of our antiderivative. T is the independent variable and y is the dependent variable. All right, so that's our family of solutions. It's underlined above. And we're going to choose the member of this family that satisfies something called an initial value or an initial condition that says that y of 0 is 3. So this just means that if t is 0, then y is 3. So how would we find the value of c to make that so? Right, so we're just going to plug in the 3 in for which one? Yeah, 3 is the y, equals negative 0 squared over 4 plus the c that we want, right? So just plug in the 0 and 3, and we find that c is 3. And so that means that I'll write it in blue again, that blue solution over there now becomes negative t squared over 4 plus 3. No, y is, like if it's solved for y, that's great. Yeah, y is still y. It's just t instead of x. Okay, so the first blue thing is called the family of solutions. The second blue thing is the particular solution that satisfies that initial conditions. Questions on that? This is just a symbol for derivative, y prime. Derivative of y with respect to t. Yeah, y prime. T is like x. Yeah, t is a variable. Okay, moving on to number 4. Let's go to Alex. Okay, so taking a look at part B, this is a different differential equation. We want someone whose derivative is equal to negative of the original function divided by 2. I don't know how to solve that at this stage, but if somebody hands me a solution, I can decide whether or not it works. And we can figure out whether or not it works by taking its derivative and seeing if it satisfies that equation in part B. So let's find dy dt for this guy. C is a constant. So we're taking the derivative of ce to the negative t over 2. Constant multiples, do they stay or disappear when you take a derivative? They stay. E to the negative t over 2, what's the derivative? Times what? Times negative 1/2, right? Chain rule. E to the stuff becomes e to the stuff times derivative of the stuff. Okay, so that's the derivative. And then, so I'll just highlight that this guy is really the left-hand side of this equation. So let's calculate the right-hand side of that same equation and see if it's equal. So the right-hand side says we're supposed to take negative y and divide it by 2. Remember, y is just the original function which was given to us. So negative ce to the negative t over 2, divide by 2. Everybody see what we did there? That's negative the original function divided by 2. So a different color, that thing right there is the right-hand side. Right, finding it is it's a different thing. But verifying or not verifying is pretty straightforward, right? And we agree that the yellow and green highlighted things down here are equal. Okay, so that means that we did have a solution handed to us. We will see one technique this class, one technique next class to solve differential equations like B today and C next class. But solving stuff that's more complicated, there's an entire course that you'll take maybe next year called differential equations. So this is just the early stages of it. Okay. This is the original function right here. That's the solution. We didn't figure it out. It was handed to us, and we just had to see if it works. It's like plugging in. Like if I say x squared equals 4 has x equals 2 as a solution, you can plug 2 in and decide whether or not it works, right? Doesn't tell you how to get there, but you can verify. Exactly. Okay. All right. So we talked about this already, but independent variable in each of these differential equations was what letter? T, and the dependent variable was y. Let's take a look at number 6. Let's go to Petru. Okay, so let's take a look at part D. It says the second derivative minus 5 times the first derivative plus 6 times y. So I'm going to copy that over here. I'm going to write it in maybe a little bit more familiar notation. It is definitely more complicated, right? Because it's a second derivative problem. So that's equivalent to part D. And so we're trying to figure out, can we make CE to the RT a solution of that if we pick the right value of R? So let's take some derivatives. I'll just copy the original, CE to the RT, y prime. That's a 5. CE to the RT times R, right? T is our variable, R is a constant. You don't need a product rule here because that times R is just another constant multiplier. And then it's going to become an R squared. Another R comes down. Because the R is a constant, C is a constant. So it's just constants times the function with T in it. Yeah, R and C are both constants. Okay, so this is really CR squared, e to the RT. So we're going to crunch everything into our differential equation here, just substitute everything back in. So instead of y double prime, it becomes this new thing, CR squared e to the RT minus 5 times what? CR e to the RT plus 6 CE to the RT. And we're really hoping we can make it equal 0. It was given. I mean, we were handed the form of a potential solution, and we're going to find R to make it so. The differential equations where if you take all these derivatives, it doesn't change very much because it needs to somehow all cancel out at the end. Okay, what can we factor out of all three terms? E to the RT, also C, and then what's left here? R squared minus 5R plus 6 equals 0. Okay, now we're getting to familiar looking things. So C is a constant, it's probably not 0. E to the RT is never 0. We just have to make this thing in the parentheses 0. Could use the quadratic formula, but I suspect this one factors. Plus 3 and minus 2. I think both minus, right? Okay, so how much is R? 3 and 2. And so if you did CE to the 3t or CE to the 2t, either one of them would be solutions to that original differential equation. Good. Let's go to Cooper for 7 on the next page. Okay, let's take a look back at number 2. The order of the differential equation is the highest order derivative. So in part D, what's the highest order derivative? Is 2. So this one right here in part D is a second order differential equation. How about part C? There's just one, just the first derivative there. Over here, A and B, both first order differential equations, right? We have that word because the techniques that you apply kind of vary depending on what order the differential equation is to start. So it's just a piece of info to get at the beginning of the problem. All right, let's go to Steve for the next one. I think it's 8. Please. Okay, so we're going to do that technique on number 9. Gabe? Okay, so let's see. We know that we're given here that the population grows. So as soon as I hear something is growing, I immediately think, oh, it's a derivative, right? It's a rate of change. So that is the rate at which the population is growing. And it says that it's growing at a rate of 5% of whatever it currently is. So 0.05. And then what's the variable for what the population currently is? It's pi. This will eventually get us to the interest equation. Yeah. So that right there captures the fact that the population is growing at a rate that's 5% whatever it currently is. We buy it? Y is the thing that represents what it currently is. It's changing. Okay, so there's our differential equation. And Steve read to us that if we can get the y's with the dy and the t's with the dt, then it's called separable. So now all of a sudden we're going to think of this dy dt as being a fraction, just a numeric fraction. And so you can multiply both sides by dt, and that dt will physically move to the other side. So how about we divide both sides by the y and multiply both sides by the dt. And tell me if you believe this is what we get. Okay. So divide both sides by y and multiply by dt. Fair? And what we've accomplished is getting the y with the dy, and the t, there isn't a t, but if there were, we would want it on the right-hand side with the dt. And so now that we have this equation, I'll put it in another color, integrate both sides, which is a fair thing to do as long as you do it on both sides. And so Sam, ln of y, yeah? And that's the integral of dy over y. Technically a plus c, but we're going to say that the plus c will just shove on the right-hand side. Antiderivative of 0.05 dt, 0.05 t. And then if possible, solve for y. All right, we'll raise both sides to the e power. So left-hand side becomes just y, right-hand side becomes e to the 0.05 t plus c. And it will really look familiar once we move that C out of this place. So I'm going to write something that you'll never need to write, but once you see it once, you just buy it forever. E to the C. Okay, we buy that. Equal, right? Because we know we keep the base and add the powers when it looks like this thing. And if C is a constant, then E to the C is just some other constant. Yeah. So how about we just call it C? It's really an abuse of the notation, but it's quite common to do. So we'll just say this is C e to the 0.05 t. And that's our PERT formula, right? Yeah. And we're going to find out that C is the starting value. At the moment, that's not clear, but you have it memorized that C is the starting value. So in number 10, it says, suppose the population size at time 0 is 100. Let's find a formula. We'll finish off that formula. So I'll copy it. Y is equal to CE to the 0.05 t. That's the formula we just came up with. The Y is the population. It becomes 100 at this moment, equals CE to the 0.05. How much is time at this moment? 0, because we say time 0, so start the clock there. And e to the 0 is 1, so how much is C? C is 100. So this is a formula that you guys have used many times before, but this is where it comes from. So sometimes it looks like PE to the RT if you're doing money. Sometimes if it's populations, it's like A0 E to the RT, or maybe some other like P0 E to the RT. Lots of variations of that formula. And that formula comes out just by assuming that the population changes at a rate proportional to whatever the current population is. In this case, it was growing at 5% of whatever the current population is. And as soon as you have that, solving the differential equation gives you this familiar formula. We use continuous growth often just because it's so easy to do, and you can typically model reality, which might be more complicated, by assuming continuous growth. Like you can get something that's close enough, and because it's so easy to do this kind of thing, we'll just say it's continuous. Okay, so I think we're good here. Let's go to just 2 more reading things and then the activity. 11 to Levi. Cameron? We have. All right. So you're going to start the activities by solving the following separable ordinary differential equation initial value problem. Right. Okay, so give it a shot. Everything today is going to be separable. Raise a flag if I can help.